Today we're diving into an exploration of how cutting-edge AI models sometimes overthink even the simplest questions. Imagine asking a world-class mathematician, what's 2 plus 3? And watching them draft a dozen proofs to answer it. Sounds wild, right? That's exactly what some of the most advanced models like OpenAI's o1-Like systems do, pouring massive resources into questions as basic as this. Here, we'll uncover why these models take the scenic route when a shortcut would suffice, and how researchers are solving this overthinking puzzle. Let's get started.
Let's begin by exploring why some large language models overthink simple problems, like calculating 2 plus 3. Here, the paper introduces what it calls o1-Like models, which focus on efficiency by generating fewer tokens. Notice how that contrasts with typical models that might generate hundreds of tokens. These o1-Like systems cut down on unnecessary steps but still perform well. If you look at the bar chart on the left, you'll see o1-Like models producing far fewer tokens while matching or beating other models in accuracy. The right side graph then compares accuracy to computational cost, revealing that o1-Like models hit a sweet spot. They use fewer resources yet maintain high accuracy. This shift represents a more practical path for AI-less brute force, more intelligent design. Moving along, the paper discusses the idea of overthinking in AI. Some models emulate human reasoning by using elaborate chain-of-thought processes, which is great for complex questions, but they often do it even for trivial tasks, wasting computational effort. So how do we keep models efficient without sacrificing performance? The authors propose a new framework with fresh metrics to measure how models balance computational cost and performance. They show it's possible to streamline reasoning and reduce wasted tokens while keeping accuracy intact. Across various benchmarks, these methods succeed for both easy and hard tasks, suggesting a future where AI systems can be both smart and resource efficient. Here, the introduction goes deeper into how certain models excel at reasoning by mimicking human thinking patterns. They break down problems into smaller steps, double-check answers, and so on. This can be helpful, but they sometimes go overboard with their reasoning, especially on something simple like 2 plus 3. It's inefficient and doesn't necessarily improve accuracy. There's an example showing that o1-Like models generated nearly 20 times more output than older models for a basic math question. That doesn't help. In fact, the authors spot 3 big drawbacks. It barely boosts accuracy, it doesn't promote much variety in thinking, and it can lead to over-elaboration on trivial tasks. To address this, 2 metrics are introduced to measure efficiency from both outcome and process standpoints, aiming to cut down on wasted computation while keeping the good parts of chain of thought. We now see how the researchers propose a self-training framework to reduce overthinking. They trim down needless solutions but retain the model's core reasoning abilities. According to their results, token usage can be nearly halved, yet the model remains just as accurate, even on tough tasks like Math 500. The paper's contributions come in 3 forms. 1. A thorough analysis of overthinking and its impact on computational overhead. 2. New metrics to gauge efficiency and effectiveness. And 3. Strategies that significantly cut token generation without hurting model quality. The next step is to see how these strategies fare in different scenarios, particularly with easy tasks where overthinking is most obvious. Now, check out how various models handle a simple question. What's 2 plus 3? A typical model might just respond 5 in about 5 tokens, but an o1-Like model, such as QWQ32B Preview, may generate 13 separate solutions. It walks through step-by-step reasoning, uses a number line, counts objects, and even brings in Roman numerals. One solution might even spill over 100 tokens, while a simpler model needs only 5. Look at figure 1 here. You'll see this stark difference. 901 tokens versus just a handful. That's a prime example of overthinking. It wastes computational resources without improving the final answer, which is still 5. Turning to the experimental setup, the paper introduces 3 key datasets. First is as-div, containing elementary-level math problems sorted by difficulty and operation type. Next comes GSM-8K, which has grade school word problems with varying linguistic styles. Finally, there's MAT-500, the toughest of the bunch, featuring high school competition questions in areas like algebra and number theory. As div is easiest, GSM-8K is moderate, and Math 500 is hardest. The paper zooms in on QWQ32B preview and DeepSeek R1 preview to see how they overthink. They define solutions as distinct outputs. Interestingly, o1-Like models usually generate 2 to 4 solutions, often repeating themselves. This sets the stage for analyzing how many extra solutions are really needed. Next, we see how frequently these o1-Like models generate multiple solutions. QWQ32B preview tends to produce more solutions for simpler datasets like as-div and fewer for harder ones like Math 500. By contrast, DeepSeek R1 preview cranks out slightly fewer solutions overall and stays consistent across different levels of difficulty. If you look at the bar graph here, you'll notice most problems get 2 to 4 solutions, with very few going beyond that. This pattern suggests that for easy tasks, the model churns out more solutions than necessary, an early sign of inefficient reasoning. Now, the paper examines how the number of solution rounds and tokens used changes with problem difficulty. With simpler tasks, QWQ32B preview and DeepSeek R1 preview produce more solution rounds, often over 3. As tasks get harder, they drop below 3 rounds, oddly putting in less visible effort for complex problems. On top of that, the total tokens used stay roughly the same regardless of difficulty. This hints that the models are generating a similar amount of text even when a problem might need either much less or much more reasoning. The authors argue this supports the idea that o1-Like models are often too wordy on easy tasks without really boosting accuracy. Now, does generating extra solutions boost accuracy? According to the paper, more than 92% of problems are answered correctly in the very first round. Later solutions contribute little or nothing to correctness. Yet those initial responses usually account for less than 60% of the total tokens. Look at Figure 5 here. You'll see that subsequent rounds rarely improve accuracy. The authors suggest a new outcome efficiency metric to measure how much later solutions actually help. This metric can pinpoint just how many tokens are wasted when the correct answer already appeared in the first place. Here, the paper gives an example illustrating the proposed outcome efficiency idea. If a correct answer emerges within 39 tokens, but you look at the total tokens used, sometimes the efficiency ratio is just 4%. That's a lot of wasted output. Then there's the discussion about diverse thinking. Multiple solutions can encourage flexibility, but repeated ones don't add value. The authors introduce a distinctness ratio to see how many truly unique solutions appear, compared to all solutions generated. The distinctness ratio takes center stage now. It tracks how many unique solutions emerge out of all those solution rounds. The authors cluster solutions based on their underlying reasoning strategies. One cluster might simply state arithmetic facts, while another walks through each step or uses analogies like counting objects. Some groups even reverse check with algebraic or binary methods. This approach highlights each model's range of problem-solving tactics, but it also reveals how easily these models repeat themselves. The paper then looks at how distinctness changes as more solutions are produced. Naturally, the first solution is always unique, so it has a perfect ratio, but second, third, and fourth solutions often reuse older approaches. For instance, the third solution might be truly distinct, while the second solution is just a restatement of the first. To measure how effectively each new solution contributes to diversity, the authors propose a process efficiency metric. It checks if the fresh solution truly adds anything new to the reasoning process, compared to how many extra tokens get used up. Here, we get a detailed comparison of different models' accuracy, token usage, and efficiency. Check out the tables. It shows smaller models like LLAMA 3.3 typically use far fewer tokens and achieve near 100% process efficiency across datasets such as as-div, GSM-8K, and Math 500. But larger models, like QQ32B, churn out more solutions and tokens, dragging down their outcome and process efficiency. The problem is excessive, redundant solutions. The authors point out that focusing on the tokens that actually add diversity can help find a better balance between brevity and variety. This part emphasizes how o1-Like models struggle with efficiency compared to more conventional ones. They generate longer responses but don't gain better accuracy or diversity. For simpler tasks, o1-Like models waste considerable effort on unneeded solution rounds. A table comparison illustrates that even on easy sets like as-div, token usage balloons with these models. That's the overthinking issue in a nutshell. The authors then pivot to discussing potential fixes, like self-training, which refines a model's reasoning process to reduce unnecessary steps yet maintain accuracy. Look here to see how two o1-Like models handle different math problem difficulties. The paper separates efficiency into two angles: process efficiency, how well the chain of thought is managed, and outcome efficiency, how many tokens align with correct answers. Graphs indicate that while process efficiency remains relatively stable, outcome efficiency actually gets better on tougher problems. Easier questions, ironically, suffer from more wasted tokens. Using QWQ32B Preview as a test platform, the authors train on specialized data to help manage how many tokens the model produces. Now, the paper tests responses under different conditions, like greedy search and sampling the shortest versus longest response. Shorter answers consistently come out on top in accuracy and resource usage. Then they discuss post-training improvements, such as supervised fine-tuning on synthetic data to align predictions more closely with the desired outcomes. They also mention direct preference optimization, where the model learns from human feedback to produce answers that people prefer. All these methods aim to refine models so they generate concise, effective solutions without extraneous computation. Here, two advanced optimization methods step into the spotlight. The first is called reasoning preference optimization, which adds a penalty term to guide the structure of the output without harming its quality. The second is simple preference optimization, which focuses on syncing model outputs with human-preferred answers through adaptive tweaks. One interesting trick is using the model's own longest response as a negative example. This gives a direct contrast that helps the model learn to avoid long-winded answers. If you check the table, you'll see how these methods boost efficiency. Strategies like producing the first correct solution with a bit of reflection retain accuracy but cut down on repetition. Next, the paper proposes 3 strategies to simplify responses and reduce overthinking. First is first correct solutions, which keeps only the earliest correct answer. Second is FCS plus reflection, which includes a second round of solution to ensure the model can reflect if needed. Third is greedily diverse solutions, which adds new perspectives if the second response isn't just a rehash of the first. All 3 aim to strike a balance between token efficiency and solution quality. By picking the shortest valid response, these approaches systematically trim away unnecessary output. Let's see how each simplification strategy stacks up. First correct solutions comes out on top for outcome and process efficiency, since it sticks to the initial correct answer. Adding reflection is slightly less efficient, but more robust for trickier cases. Greedily diverse solutions offers moderate efficiency while maintaining more variety in its answers. Check out Figure 8 here. You'll see how these strategies differ in the total number of solutions generated. Finally, the paper points out that simple preference optimization achieves the largest reduction in tokens, beating out older methods like supervised fine-tuning. When dealing with more challenging math tasks, first correct solutions uses the fewest tokens but sometimes falters on very tough problems. The FCS plus reflection method adds a second step of reasoning, which helps accuracy a bit more on hard questions. Greedily diverse solutions finds a middle ground, but it doesn't outperform FCS plus reflection. If you look at Figure 9, you'll see gains in accuracy alongside fewer tokens. On easy tasks, the model even hits perfect accuracy with significantly fewer tokens. This suggests there's real promise in these simplified approaches. Now the focus shifts to how different large language models and their response simplification methods stack up. Table 1 makes it clear. Llama and Qwen vary in accuracy, token usage, and efficiency. Simple preference optimization combined with first correct solution yields high process efficiency by highlighting the first correct answer and keeping tokens low. Adding reflection or diverse solutions can nudge accuracy higher while keeping efficiency reasonable. Interestingly, QN is especially accurate, while shorter responses generally reduce token use and raise process efficiency. This pattern holds across multiple datasets, including ASDIV and GSM8K. In assessing these efficiency strategies on ASDIV and Math 500, the paper compares the shortest response, first correct solutions, and more diverse approaches. The shortest response strategy uses the fewest tokens while maintaining decent accuracy. First correct solutions often boost both accuracy and efficiency by zeroing in on the initial correct answer. Reflection-based methods build on that approach for a balanced advantage. Meanwhile, the diverse solutions approach encourages variety, which can raise process efficiency. Overall, these techniques prove especially useful on demanding datasets like Math 500, where both token management and solution diversity matter a lot. Next, we see how these strategies work on more specialized datasets, like GPQA and AIME. Both are known for tougher questions, yet the proposed approach still shines. It tackles excessive token usage and improves accuracy at the same time. On GPQA, for instance, multiple solution strategies led to fewer total tokens and better outcomes. Similarly, token counts dropped without sacrificing accuracy, showing these methods can handle advanced reasoning while avoiding overthinking. This versatility makes the approach promising for real-world scenarios where computational resources are limited. The authors then validate their method's robustness on GPQA and AIME. GPQA covers graduate-level science topics, while AIME features challenging math problems across various fields. The model keeps performance high with fewer tokens on both. Afterward, the paper introduces the idea of scaling test-time computation. That means expanding the search space to find solutions more thoroughly, an attempt to mimic the broad exploration that human problem solvers often do. Current models are strong, but their decoding can be too narrow, missing potential solutions and leading to missed opportunities in reasoning. We move on to techniques for bolstering a model's reasoning by widening the search space. This can involve generating multiple candidate answers and then using majority voting or something like Monte Carlo tree search to pick the best one. The goal is to explore a richer set of possible solutions. The paper also looks at how models can emulate human reasoning, like breaking a problem down step by step or debating themselves. This iterative thinking can make answers more accurate. Notably, spending more time deliberating often does help, but as we've seen, it can also lead to overthinking if not controlled. Here, the discussion turns to combining efficiency with robust thinking. That might include token budgets or letting a model decide when to stop reasoning if it's unsure. Multi-agent frameworks are floated, where a smaller model handles simpler questions and a bigger one steps in for harder ones. The point is to train models to think more intelligently, not to cap their reasoning arbitrarily. In the conclusion, the authors frame overthinking as a crucial issue that saps resources. Their new efficiency metrics and methods help us see where waste happens. This sets the stage for adaptive computation that scales with task complexity, tackling big problems without over-elaborating on small ones. Finally, the paper's limitations come into view. First, only 2 specific systems that handle long reasoning were tested, so the results might not generalize to all similar models. Second, their diversity measurement relies on a high-cost clustering approach with a powerful language model, which can be tough to replicate. Future work aims to adopt open-source clustering for broader accessibility. Third, the validation used relatively small-scale datasets, raising questions about how these results would translate to larger settings. The authors plan to try out more extensive datasets for a stronger demonstration of the methods. They acknowledge these gaps while emphasizing that the study still provides a framework for tackling overthinking in AI, setting the stage for more efficient reasoning systems in the future. And that brings us to the end of this deep dive. We've seen how overthinking can waste resources, and how new strategies can make AI more efficient. We've looked at fresh metrics, self-training approaches, and ways to cut down on repetitive solutions, yet still keep accuracy high. Thanks for joining in, and we hope this journey into o1-Like modeling and efficiency has given you plenty to think about.